Welcome to another video. So in this video, we're going to talk about what in the world inverse trig functions are. Why would we do that? Because it's fun. Not really. It is kind of fun, but because you want to solve them eventually. Maybe you don't, but you're going to have to. So we're going to learn how functions solve other functions by using inverses. And that's really the basis of why we talk about this. Is because inverse functions are needed to solve certain types of functions. In fact, all functions. For instance, if you wanted to solve an equation with addition, you're going to need to use subtraction, an inverse operation. Something quite similar happens when we want to solve an equation that has sine in it, or cosine, or tangent. Well, we can't just divide. Why? Well, because sine is a function, not an operation. And so we need an inverse function rather than just an inverse operation in order to solve these equations that deal with these trigonometric functions that we've been dealt with. So we're going to talk about inverse functions, what they look like, why they are the way they are, being sort of a cutting off of a one-to-one to make a function one-to-one. And then as we progress through several more videos, we'll learn how to use inverse functions to solve their root functions. So how to use sine inverse to solve sine functions, or cosine inverse to solve cosine functions, things like that. So that's why we're getting into it. So the long story made very short is you need inverse functions to solve equations that contain a specific function. Inverse sine for sine, and the inverse of cosine for cosine, and etc. So let's talk about what they are. Now, if you remember anything about inverse functions, you should remember that a function has an inverse if and only if it's one-to-one. Now that if and only if, that IFF stands for if and only if. That's biconditional, means one is necessary and sufficient for the other. Well, what that means is this, put all together, is a function has an inverse if it's one-to-one. And if a function is one-to-one, it has an inverse. You go, okay, well, what in the world does one-to-one mean? One-to-one is this idea of being forward and backwards mappable. The specific definition is one input gives you one unique output. Now a function itself says plug in one number, you get out one number. One-to-one says plug in one number, you get out one number, but that number never happens again. Why is that important? Well, if you want to be able to reverse something, map it forwards and backwards, one input needs to be mapped to one output, but that output needs to be backwards mapped to one input. Think about this for a second. Parabolas do not do this. If I say plug in positive 2 to x squared, you're going to get 4. But I would say, okay, now take an output of 4, what was your input? You could have 2 or negative 2. The backwards mapping does not work because those two inputs gave you the same output. Therefore, that output could possibly give you two different inputs. It's forward mappable, but not backward mappable. It's a function, but not a one-to-one function. We need one-to-one functions that are mapped forwards and backwards so that inverses make sense. Why? Well, because in inverses, we switch the x and y. The input becomes the output becomes the input, the domain becomes the range, and the range becomes the domain. If that's true, then if we have one input giving us one output, and we reverse that, that new input, which was an output, is still going to give us that output. It's still a function. If we had one input, two different inputs that gave us the same output, when we reverse that, we'd have one input giving us two different outputs, and that is a non-function. So the whole thing wrapped up together is one-to-one functions are one input, one unique output, so that we can map it forwards and backwards, so that we can reverse inputs and outputs, and we still have functions. And in that way, we can undo functions with inverses. That's a really probably 3-video explanation of one-to-one in case you didn't remember it. So we're going to get right into it and talk about how sine is not one-to-one. And so we're going to have to restrict it. And in doing so, we create a portion of a function that is one-to-one. And this is the portion we have to look at so that inverses make sense. So all that you really need to know right now is that inverses are only possible if a function's one-to-one. One easy way to tell if a function's one-to-one is something called the horizontal line test. So imagine a horizontal line. If it hits your function at more than one spot, you don't have a one-to-one function. You have a function, but not a one-to-one. we got problems here. If we imagine a horizontal line, we hit outputs here and here and here and here, and every so often, twice a period, that we get the same exact outputs. That's an issue. That would be a very, very big issue because we do not have a one-to-one function in sine. Now, why is that important? If sine is not a one-to-one function, sine of x is what I'm referring to, well, then if it's not one-to-one, it can't have an inverse. So here's the thought process. If we want inverses so that we're able to solve equations with sine in them, well, then we're going to have to restrict this function so that it becomes one-to-one, so that we can map forwards and backwards and functions still work between a function and its inverse. We can still have that. So if we take a look at it and we go, yeah, that's not one-to-one, so it does not have an inverse, let's start cutting this. And the common way to do it is to take a part of this function that is to one-to-one. Now notice something. We couldn't do something like from 0 to pi. Why? Well, from 0 to pi, it's still not one-to-one. This has inputs giving us outputs that are repeated. You cannot have repeated outputs in a function that has an inverse. And so that's off the table. Where would we cut this? Well, from here to here, and along the x-axis, that's negative pi over 2 to pi over 2, that is a one-to-one function. So we're going to ignore all of this and all of this and just focus on this little sliver. Now, I've kind of zoomed in here a lot. This is the part of the sine function that we typically say, this is what we're building our inverse on. So this is huge, it's a big deal. That's why a lot of students struggle with inverses, is because they really don't recognize what we're looking at. What we're looking at when we talk about sine inverse, or some people call it arc sine, if you've heard of that before. Sine inverse is sine with a little -1, looks like an exponent. It's not, but we pronounce it sine inverse, the inverse of the sine function. This is what we're looking at. We're looking at a zoomed in part of sine. Now, in order to get an inverse out of it, again, you had to be one-to-one. This is one-to-one. Every input is giving you a unique, not repeated, output. It passes the horizontal line test. This is a one-to-one part of a function. But in order to do it, we had to cut it. In cutting it, restricting the domain, we're only looking at a little piece. Here's the payoff for us, is that when we start talking about inverse functions, if you have something outside of this interval, you can't do it. If you have something outside of this range, you can't do it. You can't talk about inverses. That creates a very specific domain and range for both the sine function that has an inverse and the sine inverse function later. And it's a big deal. We'll talk a lot about this. So what is our domain of the part of the sine function that lets us find an inverse? Well, the domain is from negative pi over 2 to pi over 2. That is including those endpoints because we don't run into any problems with those outputs being repeated. So we can go from negative pi over 2 to pi over 2 and have a one-to-one function. I hope I'm explaining that well enough. I hope that you're seeing that one-to-one functions pass horizontal line tests. Outputs are not repeated. It's because we need a mapping forwards and backwards that we have to have that happen. Sine doesn't do it, so we cut sine. Where do we cut sine? From negative pi over 2 to pi over 2. That's where we're going to cut it. Now our range says, well, you still do have the same range, don't you? From negative 1 to 1. This portion, this little part of the graph on this interval at x-axis still has a range from negative 1 to 1, including those. And our key points. Two of our most important key points are on there. Our quarters, the high and the low, the local max and local min. Now, technically, we don't really have a local max anymore because we're not changing from increasing to decreasing. We have an absolute max and an absolute min. That's true. But those key points, that negative pi over 2, negative 1, and that pi over 2, negative 1, they're still here. Negative pi over 2, negative 1, pi over 2, positive 1. Here's the deal. We need to remember a few things about how inverse functions work. So the first thing was when they're possible. They're possible when we have one-to-one functions, and a one-to-one function will have an inverse. That means this has an inverse. There's a few things about inverses though. Everything switches from inputs to outputs and outputs to inputs. What that means is several things I want to point out right now. Number one, if you're going to find an inverse function from some sort of a root function, your x's and your y's switch. Your inputs and your outputs switch. Your domain and your range switch. And your graph reflects about the y equals x. You might remember that. We talked a lot about inverses in some videos ago. The same things hold true. Even though it's trigonometry, inverses are just inverses. They take one-to-one functions and they switch stuff up. They say your x's and your y's change. What that means is that if I want to find an inverse function, if negative pi over 2 comma negative 1 is on my original function, then negative 1 comma negative pi over 2 is going to be on the inverse. Likewise, 1 comma pi over 2 is going to be on my inverse. I'm switching my x and my y. My domain is going to become my range is going to become my domain. My graph is going to reflect across y equals x. And we're going to get something just like this. So instead of negative pi over 2, negative 1, I have negative 1, negative pi over 2. 0, 0. Now wait a minute. 0, 0 is still 0, 0, so it goes through the origin. Pi over 2 comma 1, we reflect that, we get 1 comma pi over 2. Those are the key points for my inverse function. My domain is going to become my range. You can see it right now. This is still one-to-one. That's important. If we have a one-to-one function and find an inverse, the inverse is also one-to-one. They're inverses of one another. Now that's important for later on. That means that sine inverse is going to solve sine stuff. And sine stuff is going to solve sine inverse equations. They work together. It's like this. If you have an equation with addition, you need subtraction. If you have an equation with subtraction, you need addition. They work hand in hand to solve equations because they're inverse operations. Likewise, we have inverse functions here that are going to solve one another because they're made for one another and from one another based on this inverse function idea. So it's still one-to-one. It's still actually a function. It's just that everything changes. So let's write out a couple things about it. We can see it graphically that our domain is negative 1 to 1. Notice I'm not drawing arrows here. Why? Because if I was, well, then we would start getting this, this non-1-to-1 function. Same thing happens here. We're going to get this non-1-to-1 function. So our domain is negative 1 to 1. That's what the range here was. Remember, inputs and outputs switch. So domain and range switch between functions and their inverses. So domain is negative 1 to 1. Range is negative pi over 2 to pi over 2. That's our old domain becomes our range for inverse. Our old range becomes our domain for our inverse. Our key points are now different. Negative 1, negative pi over 2, 0, 0 for sure still. And then 1 comma pi over 2. And I hope that makes sense to you. The one thing that you've noticed we haven't done yet, we don't even know what it looks like. We haven't even know what the name of it looks like for sine inverse. Here's where we would get this from. So we have a picture of it and we know why it's sort of truncated. We cut it so that this would still be 1 to 1 and so is the inverse. We know our domain, we know our range, we know our key points. This is it. This is all that sine inverse can do. So here's what that means. If you have something on the inside of sine inverse that's not negative 1 to 1, you have a problem. It's outside the domain and you cannot deal with it. Interesting. If you have something inside equal to, sine inverse equal to something that's outside negative pi over 2 to pi over 2, you can't deal with it. It must satisfy what we have here and what we have here if we're going to solve it with inverses. That's interesting. That should be valuable to us. What we don't have is the name yet. So let's go ahead and let's remember how we solve equations for inverses. This is going to lead us in the next 2 videos from now how to find inverse functions. So if you remember how to solve for inverses, the first thing we did is we changed y into x and x into y. And then we solved for y. And you go, yeah, but how am I supposed to do that? Do I divide by sine? No, we can't do that. Why? Well, if we divided by sine, Sine is not really an operator, right? Sine is not a number. Sine is a function. And so we have to have something to undo that function. We call it sine inverse. So we're going to apply sine inverse to the left-hand side of both sides of this equation. What that looks like is looks kind of awkward the first time you see it and you go, okay, sine negative 1x. It's pronounced sine inverse. It stands for the inverse of the sine function. You can also hear it said or seen it read as arc sine, A-R-C sine. Arc sine and sine inverse are the same thing. And it looks a little weird over here, like, okay, sine inverse of sine of y. What in the world does that do? Here's like the plain English way to look at this. This says, thing that undoes sine of sine. Wait a minute, the thing that undoes sine is going to undo the sine. What are you left with? Well, if this undoes this, you're left with that. That's exactly what an inverse function does. An inverse function undoes the original function. The function itself would undo the inverse. And so, thing that undoes sine of sine leaves you with whatever that sine was. That's just why. This is the inverse of the sine function. So we say y equals sine inverse of x. Here's the domain and the range and the key points of it. Here's the graph of it even, but that's how you pronounce it. So if you want to do this, say sine inverse of x. You've just pronounced this correctly. You can also say arc sine x, and you've pronounced this, well, technically you'd say sine inverse, but you can see this read as arc sine. Same exact thing. A couple of comments about this. This is a big deal. Please remember this. This is a huge, that in our original function, sine of x was an angle. That's exactly what this is. Now, it can be viewed as a real number, yes, but on a unit circle, this was an angle or an arc length. And this was, well, let's see, that was a coordinate. That was a point on the unit circle. Sine inverse is now backwards. So look at this. Your angle is now your y. Well, this is your angle. This is your point. It has switched. Remember that inputs become outputs. Outputs become inputs. On the unit circle, our input was an angle. Our output was a point on the circle. Inverses say your input's a point on the circle, and your output's going to be the angle that gives you that point. That's a big deal. It's reverse of what this originally was. And that's how inverse functions really do work. They reverse the x and the y, they solve for the y. What that does is that makes inputs outputs and outputs inputs. On the unit circle, if the original input was an angle and the output was a point, now for inverses, the input's the point, the output is the angle that gives us that point. And that's really how we think about it. So I hope it makes sense. I hope it makes sense on why we had to cut this to get a one-to-one function, that this is the picture of it. And now that we've solved this down, we're going to move quickly through the cosine and cosine inverse relationship. I'm not going to show you this because it's exactly the same. What we're going to focus on is the domain and the range, what the picture looks like, and then what the key points are. Same thing for tangent. Let's talk about cosine and cosine inverse. We're going to go much quicker than the sine because we've already talked about what one-to-one means and the necessity of having a one-to-one function for an inverse. We just have to look at cosine, determine, yeah, there's no way that's one-to-one. That's not a one-to-one function. It does not pass a horizontal line test. So we're going to cut it. We're going to find out what our domain is on which we have a one-to-one portion of cosine, what our range is as a consequence of that, and then we'll take a look at what the key points are, what the graph of that would look like if we reflected across y equals x. So if we take a look at cosine of x, it's a little different. It's actually a phase shift of sine, but cosine of x is definitely not one-to-one unless we start cutting it. Now, there are several options, like we had with sine. There's several options where we could cut it, but probably the most obvious one is if we cut it at 0 and at pi, we'll have a portion of the x-axis on which cosine is one-to-one, decreasing where sine was increasing. That's interesting. Sine was an increasing function on which we took an inverse, and cosine is decreasing on that portion of the x-axis, that domain. So we're going to cut it here and here, and we're going to ignore all of this stuff. Why? Well, because we can't find a one-to-one function for that, not the whole thing. So we're going to cut this from 0 to pi, and I've done that here. So from 0 to pi, we have this portion on our graph. It passes the the horizontal line test. It is 1 to 1. Every input's giving one unique output on this interval. Well, that, therefore, is the domain on which we can find an inverse for cosine x. So our domain is from 0 to pi. Now, consequently, 0 has an output of 1 and pi has an output of -1, so that is our range. And we put it in order and the endpoints are also there. Yes, this has endpoints, it has to. Otherwise, when this continues, it becomes not 1 to 1 and we can't find an inverse any longer. And then there's some key points. We have 0, 1, pi over 2, 0, and then pi comma -1. When we start reversing those, here's what has to happen. Our x's and our y's are going to switch. So if we had 0, 1, a key point on the inverse would be 1, 0. If we had pi over 2 comma 0, on the inverse we'd have 0 pi over 2. And if we had pi comma -1, then on the inverse we have -1 comma pi. Also, this is kind of awkward because the y equals x line goes through our function. Remember, we're reflecting about that. And so this is going to look a little bit weird because any graph that crosses the line of reflection when you reflect it looks a little strange if it's diagonal. And so how this really looks is this. Looks quite similar to that sine, doesn't it? But it's not increasing. It's decreasing like the original function was. This is the graph of what we would call arc cosine x or cosine inverse of x. Now, the domain and the range are what we would expect. The domain of cosine inverse, well, that was the range of cosine. So our domain is -1 to 1. The range is the old domain. So the range was 0 to pi, or sorry, the domain was 0 to pi here. The range is 0 to pi on our cosine inverse. Another thing to remember, just remember that with the original cosine function, the input was an angle, the output was part of a point. That's also reversed. Inputs become outputs, outputs become inputs. So on cosine inverse, the input is a point, and the output is the angle that gives you that point. If I want to be a bit more specific, it's the x-coordinate of a point. And before with sine inverse, it was the y-coordinate of the point. That was your input. The output is the angle that's giving you that. It's reverse of this. So now we should have a pretty good feel for, hey, inverses are going to solve one another. That's the idea I want in your head. They only work on one-to-one functions, so we had to cut it. And that gives us something very important, that these one-to-one functions do not work everywhere. You have to have a very specific input, very specific range of outputs and inputs that work in this relationship. We're going to come back with tangent, take a look at what that is as well. All right, let's talk about one more. We're going to talk about the inverse of tangent. So we're going to find tan inverse. Same exact idea as what we've been dealing with. Actually really, really similar to sine. Even kind of looks a little bit similar to that. And so we'll take a look at it right now. So let's take a look at tangent of x. All right, here's the graph of tangent of x. And very, very conveniently, we already see that this is a one-to-one function. Now, it does have some other cycles to it, which I haven't shown, but a really sort of obvious domain restriction would be if we cut this thing at -pi/2 to pi/2, it's already 1-to-1. We don't have to modify this any other way. We're just going to kind of ignore all the other cycles, the repetitions of the periods that we have, the period being pi, a distance of pi on the x-axis, that this is already 1-to-1. So tangent of x on this particular domain is a 1-to-1 function and therefore has to have an inverse. And that's exactly what we find out. And that is the domain restriction that makes the inverse of tangent possible. Do remember this though. in its natural state without restricting the domain, this thing does continue forever with that same repetition. So it's not one-to-one in general until we make a domain restriction. And so that's what we're going to do right now. Kind of a natural one though. I mean, we see it's one-to-one. It's really nice to say, yeah, just from here to here, we have this nice function that is one-to-one. We can find an inverse. Now, one thing to keep in mind, with a vertical asymptote, you can't ever include that. It's undefined, right? There's no way to find this. If you try to plug in tangent of pi over 2, you're going to get something over 0, 1 over 0 specifically. That would be y over x in the unit circle. You say that's undefined. Yeah, that's why there's a vertical asymptote there, which means that we can't have a bracket. We're going to have a parentheses. There is no point on tangent of pi over 2 or negative pi over 2. So we're going to show that. Now the range also is from negative infinity all the way to infinity. And we see a few key points on this. We have this key point of negative pi over 4, negative 1. We've got 0, 0, and we have pi over 4, positive 1. Everything about this one-to-one function on the restricted domain of tangent is going to be reversed as far as inputs and outputs are concerned. So all of our key points are going to change. If negative pi over 4, negative 1 is on tangent, then negative 1, negative pi over 4 is on the inverse. 0, 0 gives us 0, 0. Pi over 4, 1 gives us 1 pi over 4. So we're going to get 3 points that are key points for the inverse function. And so we've shown that. We have a few points right there. Negative 1, negative pi over 4, got it, 0, 0, and 1 comma pi over 4. Inputs and outputs switch. X's and Y's switch between a function and its inverse. Domain and range also switch. So the domain of tangent was negative pi over 2 to pi over 2. That's going to be the range of tan inverse. Our range was negative infinity to positive infinity. That's going to be the domain for tan inverse. In fact, even asymptotes change. A vertical asymptote said you can't have this on the x-axis. You can't have that input. Well, we're going to have now a horizontal asymptote. You can't get that out on the y-axis. And so asymptotes at negative pi over 2 and pi over 2 are still there, but they change from vertical to horizontal. The last thing we have to do is graph it. So we know that the function we're building is an inverse function. For tangent, we have tan inverse or arctan. We can say that too. Our domain and range have switched. We have the graph. We know it's going to be a reflection across the y equals x line. So our graph is going to look something like this. That's about what tan inverse of x looks like. We can see that our domain is all real numbers. You can plug in anything to tan inverse. Why? Because you could get out anything from tangent. You can only get out negative pi over 2 to pi over 2 for tan inverse. Why? Because you can only plug in that interval for tangent. And so this is the last important point, the last thing I want to make. Please make sure you understand that the input for tangent is an angle. The output was a comparison of coordinates of points, y over x. So the reverse is true for tan inverse. Our input is going to be a ratio of y over x. The output is going to be an angle here. So we'd have this as a point. And that is the angle that gives the point. That's the reverse of the comparison of y over x being the output of some angle for tangent. Please keep this in mind, that I know that we have x's and y's going on in the context of what we're dealing with. Yes, x can be real numbers. That's what we are talking about. But on the unit circle, where I'm kind of making this come full circle to connect a little bit for you, is that when you look up tangent on a unit circle, you look up an angle. X stands for that angle. Or arc length on a unit circle, it's fine. It can be any real number, that's okay. As long as it's between here for an inverse, that's fine, that's appropriate. The input would be the angle. The output, what that is, would be the comparison of coordinates of the points on a unit circle. For sine, it was just angle gave me y coordinate. For cosine, angle gave me x coordinate. For tangent, angle gives me y divided by x coordinates. That's what's going on. The inverses reverse that. The inverses say, okay, give me a y coordinate. Sine inverse of that y coordinate gives me the angle that makes it. Give me an x coordinate. Cosine inverse of that coordinate gives me the angle that makes it. Give me a y compared to x coordinate. Tan inverse of that y compared to x is going to give me the angle that makes that ratio. I hope that makes sense. This is where these graphs come from, what they look like, and why, most importantly, why we have to restrict them to make one-to-one functions so that we can even get inverses. Next video, what we're going to do is talk about how to use it. So we're going to show what the domain has to be, what the range has to be, when you can actually simplify some of these expressions involving sine and sine inverse, or cosine, cosine inverse. So we'll get a little bit more complicated than that. Then after that, I'll show you how to find inverse functions of something like 3 sine of 2x plus 7. Can we find an inverse with that? So that's where we're going with it right now, just an introduction into how inverse functions are possible with some trigonometric ideas. Hope I've made it make sense for you, and I'll see you for another video.